no one has any questions, so I'll move on to the problems. How do I open up the problems? Ha, here we go. So the problems this week are actually so much shorter than the previous week. So what will happen is we'll probably finish earlier, much earlier. So like really, if you have any questions, you're welcome to ask them because there's no risk at all of going over time. So anyway, the first question goes, if radiation pressure is used to accelerate an object, should the object be perfectly reflecting or perfectly absorbing? So you can imagine like we have the sun and it's shooting out, light in every direction. And we have, like some ship, some solar ship with some solar sails out here, and it's got some big surface area here to collect radiation. So the radiation from the sun will come out and it'll hit the sail and it'll push it. So question for all of you, if we want this ship to accelerate as quickly as possible, would we like our solar sail or whatever, our object, to be reflecting or absorbing? What do we reckon? Reflection. Yes, very good. So yeah, this is exactly what I talked about in the slides, right? If it's reflecting, then there's a large change of momentum for the light, and therefore by conservation of momentum, or equivalently Newton's third law, there's a larger change of momentum, i.e. force, on the object. So the answer to A is just we want it to be reflecting. Reflecting, and if you want to give any reasoning for it to answer the why, you could say something like force is equal to change in momentum over some time period delta t, and delta p is larger for reflecting, larger for reflected light. Now, so yeah, easy question. So part B now goes, all right, a solar sail, and a solar sail is something that like scientists at NASA and whatever like actually looking into creating, right? If you get up into space and then you deploy a sail, you can just let the sun push you with its radiation pressure, and that way you don't need any like fuel or to produce any thrust on your own. You can just rely on the sun, yeah. So so we imagine now that our solar sail in our satellite, that the sail has some surface area of about 9 times 10 to the 4 square meters, that the whole thing weighs about 900 kilograms, and that the intensity of the sunlight, where it is about 1400 watts per meter squared. I don't know if that's a realistic number or not, but we'll roll with it. So if we assume that all the sunlight reflects off of it, so it's perfectly reflecting, we want to calculate the force on it. So how do we do this? Well, we recall from the slides that the force is proportional to a couple of things. It's proportional to the intensity of the light, I. It's proportional to the surface area, A. There's a factor of 2. We multiply it by 2 because it doesn't just absorb, it reflects. And then there's also a factor of 1 over C, basically just to get the units right. So this is the formula we use to calculate the force. So we plug in numbers now, right? I is 1400, so 2 times 1400 times the area, 9 times 10 to the 4 meters squared, divided by C, which is 3 times 10 to the 8. And you put the numbers in your calculator, and you can all check that you get the same number as me. I get roughly 0.84 newtons of force. So it's actually a pretty tiny force, all things considered. So then the question goes, all right, we also want the acceleration. So that's easy, yeah. Acceleration is equal to force over the mass. So it's equal to 0.84 divided by 900 kilograms. And bing, bang, bong, that through your calculator, you get something like 9.33 times 10 to the minus 4 meters per second squared. So it's actually a really, really, really tiny acceleration compared to, for example, the 9.8 meters per second squared acceleration that we experience from gravity here on the surface of the Earth. And this shouldn't be too surprising to you because, right, if it makes sense that the electromagnetic pressure, the force, isn't much because, well, you can go outside and you can stand out in broad sunlight, expose yourself, not in that way, and obviously you don't feel anything. There's definitely some pressure from the light hitting you and bouncing off, but it's not strong enough for you to, like affect you measurably. Like clearly you can affect it because it's not too small acceleration, at least up out where this device we've constructed is, but it's still an incredibly tiny acceleration. So yeah. So we cool with this? I'm seeing no objections, so I think we're cool with this. And then part C now goes, all right, if it starts from rest, how long does it take to move 100,000 kilometers? And to do this, well, we treat the acceleration as constant. So we go use the good old formula S equals ut, initial velocity times t, plus half acceleration times t squared. So the initial velocity is 0, so this term doesn't bother us. And we can rearrange for t to get t is equal to 2s over a, and then all square rooted. So now you can plug in the numbers, right? We have 2. S is 100,000 kilometers, so that's 10 to the 5. And kilometers is, to convert to meters, is another 10 to the 3, so that's 10 to the 8 meters. And then we divide by 9.33 times 10 to the minus 4. Let's square root the whole thing. And you can probably check with your calculators, but I get something like 4.63 times 10 to the 5 seconds. And it turns out that this is roughly like 5.5 days. So if you're there, you're constantly being pushed by the sun, it'll still take you like a bit less than a week to get 100,000 kilometers away from where you started. Compare this to, say, light, which moves at 300,000 kilometers per second. Light will cover that distance in a third of a second, whereas it takes you 5.5 days. I don't know if you consider that good or bad, but that tells you how fast light really does move. Long, big speed. Okay, so do we have any questions regarding this? Again, terribly sorry for my handwriting. I do not have a tablet that works for me. Still using my mouse to draw, but okay. Not seeing any questions, so I guess I will move on to the last question. And the question goes, right, you have a red dwarf star. So let's draw as red now. And it's Proxima Centauri. And it, of course, being a star, it has light just like our sun. So it radiates light in all directions. And it has